Good morning, class, and welcome to this lesson on Magnetism 3, Motion of a Charged Particle in Magnetic Fields. Today, we will be able to derive the equation for a charged particle moving in a circular path in a magnetic field. So, this lesson, I'm going to tell you up front, is going to seem a lot like mechanics because we're going to be bringing in a lot of mechanics principles into this, okay? So let's take a look at this. Let's just first talk about the motion of a charged particle. If this charged particle is in this magnetic field, if we look at this point right here, we'll call it the 6 o'clock position. We'll call it the 6 o'clock position. 6, 12, 3, and 9. If we did the right-hand rule at this point right here, the force would be directed inward. The force would be directed inward. And it would start to follow a curved path. And if we did the right-hand rule, anywhere along this path, we would see the force is constantly pushing towards the center. So if we did it at the 3 o'clock position here, right-hand rule, it would be pushing towards the middle. 12 o'clock position, it would be pushing towards the middle. And as you know, a force directed towards the center of a circle is a centripetal force. Is a centripetal force. So, when a charged particle is in a magnetic field, it will go in a circle continuously. So, let's look at our equation right now. Our equation for a magnetic field is B equals F Q V sine theta. We can assume here, just like in this picture, the velocity vector, this particle is moving in the, we'll say at this point it's moving in the x direction. It's moving in the x direction. And the magnetic field, these are arrows, the magnetic field is going into the page. So the magnetic field is really along this z-axis right here, along this z-axis. So the x and the z, so if it's moving in this direction, in the x direction, and the magnetic field is moving in the z, there's a 90-degree angle there. There's a 90-degree angle. So this is going to be the sine of 90. B equals F Q over V, because sine of 90 is just 1. Now, let's change the equation around. F equals B times Q times V. I recommend you get very used to seeing the equation this way as well, because honestly, with these types of questions, we seem to be going back to mechanics a lot. And the reality is mechanics is all about forces. So it's easier to see it this way than the other way. As you know, this is moving in a circle. So centripetal force, the centripetal force is equal to mv squared over r. So if the magnetic force is equal to the centripetal force, then that means that B QV equals mv squared over r. So from this, we can see that one of the v's cancels out. So we're left with B Q equals mv over r. And it's typical to keep this in this format where we make r equal mv over bq. So the radius of a charged particle in a magnetic field is equal to the mass times the velocity over the magnetic field and the charge. So very common, especially in the AP courses, is sometimes you don't have to even use this equation for math. You have to use it for logic strategies. So this is all about, once again, it's all about relationships and all about if you can understand the relationship between two variables. So let's think about this. If there's a larger charge on the particle, if the particle has a larger charge, a larger Q, the radius will be smaller. The radius will be smaller because Q and R are inversely related. Okay? And likewise, M and R, if it has a larger mass, then the radius will be larger. Okay? So a larger mass will have more trouble turning, which makes sense. A heavier car tends to be able to not turn as well as a lighter car. Okay? So think about that moving in a circle. So, like for example, in a common example, it's going to say, what's going to have a smaller radius? A proton or an electron? Well, if all things are the same, protons and electrons have the same charge, assume they're going the same velocity, and assume they're in the same magnetic field, what's going to have a smaller radius? An electron will have a smaller radius because it has a smaller mass. Okay, so there's one thing you want to look out. There's a lot of questions like that where we're just comparing variables like that, relationships. Okay, so this is going to be a new equation that you need to memorize because it's going to be used frequently. Now, I want to just say what we did there is we took F equals B QV, and we set it equal to centripetal force. Okay, we set it equal to centripetal force. Now, it doesn't really matter if we set it to centripetal force or we set it to anything. The question might say something along the lines of the magnetic force is going to be balanced by its weight. So if it's balanced by its weight, it would be mg equals b qv. This is the weight of the particle, and this would be the magnetic force. Or it could say it's balanced by friction. I'm not sure I've ever seen that one before, but I'm just kind of making it up just to show you the point. So it would be b qv equals mu times n. So all the things we learned in mechanics we can apply here. This is just one of many forces that we have learned about now. Okay. So one more thing I want to talk about before we finish is the concept of work. Okay. So let's review work for real quick. Work equals FD cosine theta. So if the cosine of theta is 90 degrees, then that means work equals 0. Work equals 0. Okay, because the cosine of 90 is equal to 0. So if the direction of motion, I'm going to write it over here. If the direction of motion is 90 degrees to the force, then we have 0 work done. So let's just draw this out. If the direction of motion is 90 degrees to the force, there is no work done. If the direction of motion is 90 degrees to the force, there is no work done. I think you're getting the point now. So basically, in a magnetic field cannot do work and change. It cannot do work and change the kinetic energy. Because remember, one of the things work is equal to is the change in kinetic energy. Okay, so the magnetic field will only change the direction. It will only change the direction, but it will not change the velocity. It will not change the velocity. So that's something to remember, okay? Anything moving in a circular path has no work done on it. It's changing direction, but it is not, the kinetic energy is not changing, therefore no work is being done. Okay? So that is it for understanding the motion of charged particles in a magnetic field.